Hello again. What the heck?
Tagon.
I'm gonna keep avoiding the original integral question that I still have yet to answer. I'm working on it. Today we're going to prove sort of a preliminary theorem that I need for other things down the line, and that is simply derivatives and integrals, definite and indefinite, of inverse functions. So let's get into that. Okay, so this is the kind of question that I would like to answer today. So given a differentiable function, f of x, which means that it's sort of smooth everywhere, we can sort of tell what the slope of the function is at any point, depending on what your domain is. So given a differentiable function, little f of x, and another function, capital F of x, such that the derivative of capital F of x is equal to little f of x. In other words, capital F of x is just the antiderivative of f of x. We're simply saying that this function does exist. So given those two functions, we want to determine what the derivative of the inverse of little f is. So a general function f of x, a general differentiable function f of x, we want to know what the derivative of its inverse is. And so that's given a difficulty of 1 question mark. And then we also want to find out what the antiderivative of the inverse of little f of x is, and that's given a difficulty of 2 question marks. Now I don't know that that actually reflects the difficulty of the question. We're just going to do this one first and then use that answer to inform the answer to this question here. Okay, so let's see if we can attack these problems. So we're going to have to employ something called implicit differentiation, which is when you simply don't have the dependent variable explicitly solved for in terms of the independent variable, and you still can do calculus to it. So we're going to define y is equal to f inverse of x. Remember, we're given a function f of x, little f of x, which means this implies that f of y is equal to x, right? But now we can take the derivative of both sides, so this implies that what's the derivative of x with respect to x? Well, that's just 1, right? Basic power rule. Because we know that f is differentiable, we know that we can just do f prime of y, but then we have to multiply by the derivative of the inside, which is what the chain rule states, right? So we have y prime. And now y prime is what we're looking for, right? Y is the inverse of little f, so we want to find the derivative of y. So we divide by f prime, and we get that y prime is equal to 1 over the derivative of little f of y. But what is this? What is y? Y is the inverse of f of x. So all we have to do to get the final answer in terms of x is replace y with f inverse. So we get that the derivative of the inverse of a function is equal to 1 divided by the derivative of the function evaluated at the inverse. Now that's kind of a mouthful, but let's just review it one more time real quick. So we've defined y to be equal to the inverse of f. So then we applied the function f to both sides of the equation so that we got f of y is equal to x, because f and f inverse will cancel and just give you the input back. Then we took the derivative of both sides with respect to x. The derivative of x is just 1, and because y is a function of x, we have to employ the chain rule here because we have y inside of another function. So because we allowed for f to be differentiable, the first part is just the derivative of f with respect to y, and then we take the derivative of y on the inside with respect to x, right? And that's sort of just implicitly understood. We are looking for y prime because I want to know the derivative of the inverse function of f. So we have to divide by the derivative of f with respect to y on both sides to solve for y prime. And that is equal to 1 over the derivative of f with respect to y. Because y is equal to f inverse, we just plug f inverse where y is. It's a composition of functions. So it's 1 over f prime composed with f inverse of x. That's a valid way of writing it as well. So it's f prime, the derivative of f, composed with f inverse applied to x. So that's another way of writing it. But this is the derivative of the inverse function of f. So now let's calculate the antiderivative. So we're going to have to do a substitution in this one. So we want to know the antiderivative of the inverse function of x. I think it seems natural that we're going to say let x equal f of t, in which case we will get dx, taking the derivative on both sides, we'll get that dx is equal to f prime of t dt, pretty basic calculus there. And then we simply just replace everything here, and we get what? We have to plug in f of t where we see x, so we get f inverse of f of t, so that's just t. And then we have to replace dx with this new, with the the determinant of the 1 by 1 Jacobian matrix here, and that's just writing f prime of t dt. And now all we have to do is do integration by parts, which is not too difficult. Because this is already a derivative, let's integrate this and take the derivative of that. That seems to make the most sense. So we set up our little chart, t differentiated becomes dt, and f prime of t dt gets integrated to become f of t. Do our little integration by parts, and we get t times f of t minus the integral of this times that. So minus the integral of f of t dt. I can erase this now that we've done our integration by parts. This can be simplified, right? We were given both that little f is differentiable and that it has an antiderivative, capital F. So the antiderivative, the integral of little f of t is just capital F of t, right? That was plus a constant because it's an antiderivative, not a definite integral. So we get t times f of t minus capital F of t plus a constant. But we know we can solve for t in terms of x. So because x is equal to f of t, that means that f inverse of x is equal to t. So if we plug f inverse of x wherever we see t, then we'll have our thing in terms of x. So if we plug f inverse into f of t, we get f of f inverse of x. Those two functions cancel because they are inverses and we just get x back. Then we plug f inverse into t there, and so we get that. And now the last place we have to plug it in is in here. So we get minus capital F of f inverse of x plus a constant. And likewise with the derivative, we can write this nested function using the composition of functions notation. So we have x times f inverse of x minus capital F composed with f inverse of x plus a constant. So both of those are perfectly valid ways of writing this answer. And there's one more thing I want to show you, which is actually something to do with a definite integral of the inverse functions. So that was a lovely fact. I'm glad I got to show that. And now we can do something with the definite integral of an inverse function. So imagine we have some function, right? It doesn't matter what it is. And we have some input x equals a, and we have some other input x equals b. So this is some function f of x. Right? This right here, this curve. Well, then this is f of a, right? This is y equals f of a. And this right here is y equals f of b. And right, these things don't necessarily have to be in this order. B could be less than a, f of b could be less than f of a. That's not really the point. The point is we can write these areas in terms of the function and its inputs, because the area under this curve from a to b is simply the integral, the antiderivative, from a to b of f of x with respect to x. But you'll notice we also have this pretty clear area right here.
Interval.
Right, this more horizontal looking section here. And if we actually switch the variable here and switch to y's perspective, and we consider this to be an integral from f of a to f of b, like the bounds of an integral, what function might this be the area under? Well, as it turns out, it's the inverse of f of x, which makes sense, sort of, because we're sort of switching our perspective from x to y, thus flipping which one is considered the input and which one is the output. And so it should make sense that the area that you get from the function left towards the y-axis is simply the area that would be under the inverse function of x, because if we flipped it over the line y equals x, we would end up with this area down here, like a normal function. So we can actually add those two areas together. So this becomes the integral from f of a to f of b of the inverse of f with respect to y. And we can actually say what this equals, right? Because what we have here is just a big rectangle, right? It's a big rectangle. And the whole thing is the length b times the length f of b. So the area of the whole thing is b times f of b. But notice we're not including this little rectangle here. And the area of that is a times f of a. So we can say that this sum of integrals, the one that's over the regular function from a to b, and the one that's over the inverse function from the function applied to a to the function applied to b, this is simply equal to this is simply equal to b times f of b minus a times f of a. And I think that's such a neat little fact there. It's very lovely. So that's the third fact presented in the video. So that's going to be the end of the video. I'm just going to rewrite all of these things now all together so that we have a clear list of what we've learned today. So we've learned that the derivative of the inverse function of f with respect to x is equal to 1 divided by the derivative of f applied to the inverse function of f. Sort of compose the two functions together, f prime of f inverse of x. We learned that the indefinite integral of the inverse function of f with respect to x is equal to x times f inverse of x minus the antiderivative of f inverse of x plus a constant. And we learned this neat fact that if you take the integral from a to b of a function f and you add to it the sort of vertical version from f of a to f of b of the inverse function, and I'm writing it with respect to y to sort of motivate that looking from the perspective of the y-axis, then you simply get b times f of b minus a times f of a. So these are 3 awesome facts that I derived today in this video. Thank you for watching. I hope these are really interesting. We're going to be using these facts later on to solve some very interesting integral questions. So I'll see you in the next video. Thanks.
Interval